Welcome to the last lecture of, wow, I sound really loud. Okay, welcome to the last lecture of machine learning. And in this lecture, we review everything that we've learned. It's kind of crazy that we're at the last lecture. Time has really flown by. And yeah, so I'm told I'm supposed to tell you guys to fill out the survey. And I thought I was just going to say like a couple seconds and be like, do this on your own time, especially when all the other people watch this stuff. And then I thought about it, and I feel like, I don't know, I decided to say more than 2 words. So I'll tell you like a minute or two about the survey thing. So yeah, I thought back, and like in my undergrad, I never really filled out the survey, to be honest. Maybe I did it like once or twice and stuff. And I thought about why, and like the two kind of reasons, I guess, is like, what's the point of the survey? The main point of the survey is really to help people in the future, right? It's like the future, like it's not really going to benefit you. Like you're done the course. So there's like one benefit is like you're going to help the future classes. But then there's one big caveat, which is that the instructor actually reads this, and then they're the instructor for next term, and they're actually going to change things and so on and so on. And so like the first point I can't really help you with. You make that like decision for yourself, whether you want to help others. Like it's completely optional, doesn't change your life. But the second point, I can actually assure you that I think the changes will actually like take shape, and I can actually make things happen. So next semester, this course will be taught, and I'm actually the TA for the instructor, which will be interesting. So I can like push them to make them, we're going to follow like the same course and whatever, so we can make the changes. And then I'll probably I'll probably teach this again next fall. So like, I'll actually make the changes. So I can promise you that. Okay. And other thing is like, what should you tell me, or like what's useful information? I guess like teaching part, yeah, that's all helpful so I can improve my teaching. But also just like, it's useful to know like what you guys thought of the assignments. Like if you thought if you thought having everything multiple choice was not a good idea and things should maybe be changed. If you thought having like, I don't know, if it got too hard at the end, maybe it was too easy at the beginning, was too much math, you wanted more of something. Everything is good to know because we can actually make this change for the future people, you know? So help the students of the future. Okay, that's all I have to say. So yeah, do as you wish. And now we begin with the review of the exam material. Okay, so as you might have seen, yesterday I made an announcement, which is like very similar to the previous announcements, but with some specific information to this final exam, obviously. Important points is like, make sure you come on December 18th and not on a different day, and that you come at 8:30 a.m., and that you show up to Pavilion, which I guess is the Butter Dome. And we have some certain rows, which I told you what rows, but I guess if you show up, you're going to figure it out. Okay, that's the important thing to make sure you get to the correct location. Okay, so the exam's 3 hours, as you see, and it's 40 multiple choice questions, which I think is quite reasonable because that actually gives you more time to do each question than you would have had on all the midterms. Okay, now what's the breakdown of like what content you should know for this final exam? So it is cumulative, which I don't know, I chose to make it cumulative. I think that makes sense. And it's like, I guess, an emphasis on the second half or whatever of the course, which also seems to make sense to me. So yeah, so this, okay, what's the breakdown? There's like 3 parts. This is the stuff before midterm 1. This is the stuff from midterm 1 to midterm 2. And this is the stuff after midterm 2. So in terms of new stuff, 40% of the stuff is after midterm 2. And then the other 60% is stuff before midterm 2. So this is stuff that was on midterm 2. This is stuff that was on midterm 1. Yeah, so that's the breakdown, I guess. So studying, so like, honestly, like there's 40 questions, so the plan is to kind of ask a little bit of like every topic in the course. Like that's kind of the beauty of also having this many questions, and you have you don't have to write, so you can ask more questions, and you have we can actually cover most of what's covered on the course, which means that like you don't get this situation maybe with other exams where like you study one section really well and another one, and then you get asked the stuff you have no idea about. So here you can like expect that everything will be kind of be covered, I guess, as you've seen. And what's the best way to study? It's, as I guess I've said before, like the questions you should have seen on the midterms are very similar to what you see on these assignments and examples, and the final will be very similar. So like review the assignments, there's the solutions posted. Review the examples and exercises, there's solutions for that. And then I guess some people like asked me to add some more exercises on Piazza, and I will try to do that. And then if you ask for more on certain things, I can also try, but we'll see how much time I have over the coming week. But like, yeah, feel free to ask. And maybe I can make like a video on YouTube as I've done for some of these things if it's helpful. So I will try what I can. And then, yeah, midterms, there's also solutions for those. So obviously go over that. And then make sure you know your formula sheet. I posted what the formula sheet is. If you really think something important is missing on there, let me know. If not, like all the stuff should be put in the question if you need details anyway. So if it's not on there, you can expect the details to be within the question. And other than that, that's everything about the final like high level overview. Okay, some other small notes about the stuff before. One thing I wanted to mention, so I got a little carried away with this whole softmax neural network business, and I thought about it a little bit more, and I kind of lied to you guys. So you can actually implement softmax with a neural network, but you have to take like many layers to do it, and it's possible, and I think it's fine, and maybe I'll add the exercise to the course notes so you can see. But you definitely can't do it with these like single layer neural networks the same way you've seen with like the logistic function and the linear function stuff. And so people still do this like post-processing thing, and they don't say that, oh, like I'm gonna add like 5 more layers of my neural network or something to do this. But yeah, that's just something I wanted to point out that that is not right. And I fixed it in the course notes as well. Okay. Other thing is that I noticed in the course notes as I was just reading through some part that maybe this could confuse some people, but like I guess you should have known you should see from the equations, but just one note is that this D superscript B is the number of non-biased neurons. So it's like every layer will have this many plus 1 neurons except for the output. Okay, so just like in terms of terminology, I called it in the notes, like I said, this is the number of neurons in a layer B. Like technically it's the number of non-biased neurons because you're gonna have this like plus 1. Okay, so just like terminology, I guess it's useful for you when you're answering questions about how many neurons are there or activations or weights and stuff like this. Okay, and with all of that being said, I will go into the review, but maybe there's some questions before. Okay, let us do the review. So I thought about how to do this review, and somehow the best solution I came with was to copy and paste the past reviews and then add more to the new stuff like that we covered. And I'm just gonna skim through the past stuff because I think all of it is like definitely gonna be related and asked in some way, but maybe I'm gonna like skim through all the stuff you've seen before and maybe point out the main points of it. Because I decided that you having the whole note as one thing is probably more helpful maybe to study than just a few bullet points. Okay, so what was the story of the whole course? It was something like, and maybe I answer the question before I get started. So the question was something like, for the final exam, is there anything else we need to know other than our new exam location if we have exam accommodations? I do not think so. And if there is, I guess I'll make a post, but yeah. Okay. Yeah, I will really, hopefully I don't miss anything with this final exam stuff, since it's all new to me as well. Okay, let us begin the review. So we started with learning math so that we can do machine learning, because as you saw, there's a lot of math. So what did we need to know about math? Well, we need to know like all this different notations about how to represent sets and Cartesian products and so on, and all these, you saw this stuff, like we had to talk about elements of things, subsets of things, we had to define sets of functions. So this was all useful, and you might get asked some questions on just like this basic stuff, because, yeah, I mean, obviously you'll need to know it for future questions, but you can get some marks by at least knowing this, the basics before being applied to machine learning. So you could expect to be asked about like the simple math stuff. That's like the kind of the easy 20% you get at the beginning of the final, I guess. Okay, so then you learned about these dot products. You saw how useful these are. This is kind of like the basis of all this machine learning stuff and even neural networks. Like every layer has this dot product being applied. And then we learned about these functions, and there's different kind of functions. There's the functions you've seen before, which are like taking in just like a number and then outputting a number. Then you saw that you could have functions of like multiple inputs, so vectors, for instance, like the softmax was taking in this vector input. And then you could even have functions that output functions, and this was like the learning algorithm or the learner, right? It would take in a data set and output a model, a predictor, a function, all the same word. And that kind of has this type of representation. And we spent some time on that. Okay. Then we talked about this math stuff of summation and integration. And summation, this is just like very useful symbol. You've seen this a lot again in the course for all sorts of notation with even just like defining the dot product, you use the summation symbol, talking about all the data points in the data set. So this summation you saw comes up a lot. And so you should be familiar with how to do that. Integration, you might have noticed, actually didn't come up that often. And That is in part because we didn't go into the details of how to like calculate what F base is. That's where I thought this would be very, well, that's where it becomes useful, but I then realized we weren't going to go into the details. So you didn't see as much of this. So, but just to like remind you why this would be useful in machine learning, there is this expected loss function, and you might remember that the expected loss, especially if the data is like continuous, which at least the features are, there's these integrals and these sums, and you get these sort of like you get this integral sum stuff. But anyways, we didn't end up working out too much of this in the course, so you probably won't see much of it. Then there was partial derivatives. This clearly was very important and potentially should have been emphasized more at the beginning of the course. You can tell me in the course review, because then we got into these detailed partial derivatives after that were probably much more complicated than what you saw in the review or like the math review stuff at the beginning. But of course, this is very important. So you might get asked just like a straight up partial derivative calculation with no context of machine learning stuff, just to see if you know that type of details. And yeah, there's a lot of like common derivative rules and stuff on the formula sheet, but the main thing you're probably going to need to know how to do is apply the chain rule. You've seen that a lot. Okay, then we moved into the probability world. And the probability stuff was important for like MLE and map stuff, but it's usually these like, you represent your data, saying that it's like random and things like this, and then you need like certain like tricks from probability, where like this product rule or Bayes rule and stuff to manipulate the formulas to then get something simpler that you can then take like derivatives of or like minimize and things like that. Okay. So what did we learn here? We learned that there is something called like an outcome space and an event. An event is just a subset of this outcome space. This is outcome space, this is event. Then there's something called a probability distribution. This is the thing you really care about. It's like the probability of an event. And you think of this, it's like the probability that an outcome occurring belongs to this event, element of that set. So it's a function that takes in events, outputs probabilities of that. So that's a number between 0 and 1. Turns out like that's a thing you really care about, but you never really work with this function because it's complicated. It has like, there's lots and lots of possible events. So you end up using, okay, there's like all sorts of notational definition stuff. Like the random variable equaling x really means that the random variable is in the event that contains just that thing, and so on. You can review this stuff. Okay, but the point is that to work out these probability distributions, you really end up using something like a PMF or a PDF. That was the kind of the story. These are the functions that help you calculate these things. So you never actually really end up working with the distribution itself. You work with these PMFs or PDFs, and this depends on if your random variable is discrete or continuous. And discrete random variables like means that the outcome space is countable. Usually, well, what that means is like you just have like a finite set of objects in the set, or you have like there's a one-to-one map with the natural numbers, but really you'd only see the natural numbers, and probably you won't even see that in the questions. So like really you should see finite set of objects. That's like your discrete outcome space. That means your random variable is discrete. Otherwise, if it's like the reals or like the intervals or something like this, then it's a continuous random variable. And that immediately tells you what you should use for calculating probabilities. You should use the PMF or the PDF, or like what is it going to have? Okay, and in like the way you calculate these things is that the probability of your random variable belonging to this event, so like that's like your outcome that actually happens belonging to this event, is then calculated as the sum of the PMF over all of the elements of the event. Okay, we've seen this many times. And then the integral, I guess the integral comes up here, whereas in the continuous random variable case, you use PDFs and then you integrate over them. Okay. And then there's some commonly used distributions. These are clearly useful for MLE and MAP, as you've seen. And some of them are like the Bernoulli, the normal, the Laplace. And I've added to the formula sheet the I think this is how you spell it. Probably. Okay, categorical distribution, just so you remember the parameters it has. But yeah. So that was the one thing added to that table in your formula sheet. Yeah, and then we went into like, you can talk about random variables that are tuples of other random variables. You call these multivariate random variables, or like multi-dimensional random variables, where each dimension is one of the random variables. And then there's like very similar formulas that kind of apply to all this, and we've seen it before. And on your formula sheet, you have this like joint distributions, which is the distribution of both the random variables. Then you have the case where you only talk about one random variable and have all the others fixed. And then the conditional one, or sorry, not the other ones fixed, but you don't care about them. So you take all cases of the others. Then there's the conditional one, which is actually the case where you like fix another random variable and then talk about a certain random variable. So you're like conditioning on the variable. And there's very similar formulas to calculate all these using a PMF or a PDF. And there's like joint PMF PDF, conditional PMF PDF, and marginal PMF PDF. Okay. And then a very important rule that we've seen a lot in this MLE and map stuff is this product rule, which tells us that if you have this joint PMF or PDF or the kind of the mixture of both of them sometimes, you can then write it as the conditional times the marginal and in both directions. So you could condition on X and then multiply by the marginal of X or the other way around. This obviously, once again, came up a lot in MLE and map. So yeah, you could expect to be asked some of this, like maybe some simple stuff similar to what you've seen on those early assignments, just to make sure you understand when to use kind of what and stuff. Okay. Oh, another very important property, probably like the two kind of most important ones we see, is this product rule being used throughout the course and this independent stuff. And this independent stuff comes up where like the feature label pairs in our data set are all independent of each other. So what that means is that we can write this giant joint PMF or PDF of all the data as this product. That comes up in MLE. Remember, it's like you have this like likelihood function. It's like the little p of d of the data, and then you write out the data, and you're like, oh, all these are IID, I meaning independent, and then identically whatever. But the I means you can do this, the independence, and then the identically distributed meant that these p's were all actually the same. Also comes up in map because you usually assume that these weights are all independent as well, and then you write out their product. Yes, okay. So two very important things. If you don't know them, you're probably kind of screwed for all the other parts in the future of the questions. Okay, functions of random variables. So yeah, like if you have a random variable, you take a function of it, it's still a random variable. This like comes up when we talk about the loss function being applied to x and y, still being a random variable, and then like the sum of those still being a random variable and things like that. So just know that piece of information. And then kind of the last thing I think that was done in this probability stuff is this expectation and variance business. And here, yeah, there's expectations of random variable. Okay, there's this case where you take an expectation of a random variable or of a function of a random variable. That's also just a random variable. So this could really just be grouped as one case. But what was the story here? It's like you should think of this as the average value that random variable takes if you had like infinitely many samples of it. Okay, so it's not the one that you expect the most likely. It's like the average of all those values, and you take that. So it might be something that doesn't even occur. So like important things to know. And then once again, if you want the multivariate conditional versions of these, you just like the formulas end up being like the value of random variable times its PMF PDF, and then you integrate or sum. So like all these things are on the formula sheet. And then the variance, roughly speaking, is like how much the random variable varies relative to its average or expected value. Okay, and then there's this formula. So that's like the intuition you have of the variance, and then maybe you should know how to work out some of these for very simple cases. If I like give you the expectation, you just like kind of plug this into the equation and work some things out. Okay, then we finally did all this math stuff, and I kind of told you how it connected to things. And then we finally got to defining the actual supervised learning problem. And somehow my computer has disconnected from the call again. But from my past experience, it will reconnect and everything will be okay. So I shall continue. So yeah, so we got to the actual machine learning, or like a specific machine learning problem, which is the most common one, is the supervised learning one. And that's the one we focus on for the whole course. So we never diverted from this really. And this is the story we had in supervised learning, which was that you had a data set. It was a bunch, and by a bunch I mean n feature label pairs. These are feature label pairs. And here was the assumptions that are directly related to what we just saw. Feature label pairs are independent, meaning each one of these is independent of one another, and they're identically distributed. So they have the same distribution here. So this allowed us to use this like product rule property, and that the little p's are all the same. We really saw that in MLE stuff later on. Okay. And then we called this these like feature vectors, like the set of feature vectors, and this the set of labels. And maybe I should have put feature vectors and labels or targets. Okay, and then so this is like the thing we're going to use to decide on what we want to, like, what's the model we're going to produce and so on. This was like one object in the supervised learning problem, I guess. The thing you want to do is design this learner or define this learner or whatever, such that it takes in a data set, right? This is the set of all data sets. So it's going to take one of the data sets in that set, and then it's going to output a function in this set. And okay, like what do you want from this learner? So that's what it's going to do, but like what does it mean for it to output a good function? Okay, so like this is the thing it outputs, the function, the predictor, the model, all the same thing. And then we said that what it means for it to do well is for, okay, so there's like, let me go straight to the objective here, which is for this learner to do well, it means that on average, over all data sets, it will do well in terms of the loss function on average over all the data points, okay? So there's like two things. So like there's outer expectation is talking about the average function, or like what is the predictor or the model your learner will output kind of on average over data sets. So now you have a predictor, okay? And now you want to ask, how well does that predictor do on new data? So that's what this capital L does. It talks about in expectation, how does that predictor do on average over new data? So there's like these two kind of nested expectations, can get very confusing. And yeah, so what is, once again, that inner one, quite important. This is the one we mainly focus on, and only talk about this when we talk about like this evaluating models and so on, is this inner one depends on this loss function, which kind of measures how good is your prediction. That would be like this first input into the loss function relative to the true label. So you'd like pass in your predictor for a given feature, and you compare it to like this true label. And you do that on average over all possible data. And that gives you the true expected loss. And the claim was that this number is a good representation of how well your predictor is doing on new data. And you want to make that small. And if you believe all that, then we can talk about how to achieve this goal. And before we do that, apparently there's two classic ways to break down the problem into like two subclasses so that it's easier to work with, I guess. And this is called regression and classification. Okay, so bear with me before I get to how to solve this problem. So there's the regression case, which is the labels have a notion of order. Usually this means they're like an interval or the real numbers. That's what we saw. So being like, there's a notion that like some number is closer to another number, as opposed to the classification case in which the labels, there's no notion of being closer. Like if the labels are like, for instance, the words, we saw this in language models. If I predict one word, okay, the claim is that there's no real notion that that word is closer to the correct word than another word, even though, as you can see, that might not be entirely true all the time. Okay, so that was the idea, and then this changes the loss you should use. The squared loss somehow measures how close things are, while the 0-1 loss really doesn't. It just says like, you're either right or wrong. Okay, and then we got into how do we solve this, like what is the actual learner we're going to use, and that was called ERM. And we basically saw that every single learner can be thought of as ERM with a different function class or a different loss function. And that's quite beautiful. And then you talk about how do you like optimize as well within it. And okay, let me mention what ERM is properly, which is there's two steps to it, which is the first step is like you don't know what the expected loss is, so instead you estimate it with data. And that's, you use this thing called an estimated loss, LHAD. And there's like various ways you could do that, and that will also obviously depend on the loss function you choose and so on. And then after that, you want to make this thing like if you believe, I guess, that this thing is actually close to this, it would make some sense to then find the function that makes this the smallest. Because if you can make that the smallest, then you would claim that, oh, maybe this thing's also really small. And so the way you do that is you search over the set of functions or the set of predictors. And what you find is that like if this class is really, really big, it's very hard to actually optimize over it. So what we always saw is that we picked this class in a very special way, such that it could be described by some set of weights, right? And this is always the story. It's like, I don't know how to optimize over functions, which is what I'm trying to do. I'm trying to pick the best function. So instead I say, okay, every one of my functions can be described by like some number or some vector or something. And now I know how to do this, which is what we're going to get into in this optimization stuff. And so that was really the story of the whole course. It's like, no one wants to optimize over functions. I don't even know what that really, that's like, like you can do it if you have some finite set of functions, but if you have this like giant set of functions, like what are you going to do? So you say there's a parameter, one-to-one like relationship with a parameter and function, and you search over this. And I still can't connect on my computer, but okay. So then we got into optimization world. Oh, we actually got into estimation world, I guess, first. And this was relating to the first step, and this was really simple. And the interesting thing, okay, maybe I mentioned one note, is that here we barely talked about this, right? We just like very briefly, as you'll see, there's like one page, said that, oh, we just estimate this thing, and like how are we going to do it with a sample mean? And then we kind of say that it's probably fine and move on. It turns out that like in these kind of like undergrad course and stuff, a lot of time is spent, and even like in like a lot of practical applications, a lot of time is spent on this optimization stuff, as you saw. Like almost everything was talking about this. But there's a whole other field of theoretical machine learning, where they call like statistical learning theory, and there they like almost the whole courses focus on just this step, and they don't really care about this. They just say, oh, you like assume you can do it somehow. And so they really focus about like how do you best estimate? How do you really ensure that your estimates of things are good? Then if you have that, then you're like good to go with the optimization. You figure that out in your practical world. Okay, so I just wanted to like kind of put in context where things stand and why we didn't really talk about it. That requires a lot more like probability theory and so on. So usually not covered in early courses. Okay, so anyways, all we said was you want to estimate this thing, but you have samples. So what you do is you basically use the sample mean. Okay, that looked something like you'd sum up all of the random variables. Here it's going to be like your loss function plugged in with the predictor on the corresponding feature and the label. That would be your random variable, and you sum all those and you divide by n, and then you get the sample mean estimate of the loss or the expected loss. And there were some nice properties about this. If the random variables were independent and identically distributed, which is like the expectation of this sum of random variables divided by n is actually the expectation of each one of the random variables, which is really nice, and that the variance goes down with n. And then we saw that like this is not quite true at the very end because you pick your predictor based on the data. But for now, this was like the hope that things would be okay. Okay, then we got into optimization, which was like the big chunk of things. How do you actually, oh, I can finally connect. Great. So I think I missed all of the comments and questions, unfortunately. So maybe you can re-ask those and I can try to address them. Okay, we got into optimization, and maybe I should speed up a little bit. Okay, so we got into optimization, and this was the optimization part of ERM. And then there was like discussions about how you do optimization. So this was like stepping away from machine learning first, just saying like, how do you do optimization? And then we jumped back into machine learning. So I guess the stuff you guys really care about is like, what would you be asked on the exam? You can, I guess it's not that helpful to say that like, you can be asked any one of these things. Like you might be asked this, like just these optimization things. Like, is this argmin really equal to this as like one of the options of things? So you should know all this because it all connects. I don't know how helpful that is, but yes, you could really expect to be asked any one of these things that I'm saying. Yeah, so we started with saying, what is optimization? Optimization is you have a function that depends on something, like any function does, and your goal is to find when is the function its largest value or its smallest value. And we always talk about minimization, just for like consistency everywhere. And so you write something like the minimum value of the function over some value w. Okay, that was the main story. And then it's the minimizer is this w star variable, or like it's the thing that makes the value of the input that makes the function the smallest. And we call this the argmin, like the minimum argument, the argument that makes the function the smallest. Okay, and we saw there's kind of like two branches of optimization. We didn't talk about the first one, which is discrete, but in the discrete world, there, if the function just has some finite number of things, you can just compare all those values and pick like the smallest one. But in general, your function can output like a whole continuous number of things. And so there you're going to use derivatives and so on, and that's what we talked about. Okay, and there's some special cases in which optimization works out really nicely. And those cases are when this function is convex and you can take the derivative twice, okay? And so like what does convexity means? It means that the second derivative is always greater than 0, or greater than or equal to 0. And yeah, so that's what convex means. And then there's two cases to do this optimization. And it's like you look, if your domain is all the real numbers, then the solution is just always going to be the point at which the first derivative is 0. However, there's this other case in which the domain of your function might be some interval, in which case you still solve for the derivative and check if it's 0, but you have to check if the point w that achieves this point, this thing, is actually inside the interval. Because if it's not, then you find that you have like what is called like a constrained optimization problem, and you have to check the end intervals and pick that. Okay, and we didn't see that too often in this course, but in like further courses, you actually do find that there's people will work with these type of constraints on the optimization and stuff. Okay, so we mainly worked with this first case for everything kind of down the line. Right, and then that was the one-dimensional case, and then in multi-dimensional world, things kind of are the same story, except the one thing is, I don't tell you how to check for convexity. The story is actually kind of similar. You do take these second derivatives, but now you have a matrix of second derivatives instead of a number. You didn't have to learn any of this, and so I just tell you when things are convex in the second derivative, in the multi-dimensional case. And so if things are convex, then you can calculate the minimum or the minimizers of functions by doing a very similar process to before, which is now you might have like a multi-dimensional, well, you are going to have this multi-dimensional vector you're trying to solve for. And the way you do it is you solve for each dimension kind of independently, in the sense that you set every partial derivative to 0, and then you have to solve this giant system of equations because usually the partial derivatives will all kind of depend on each other. But then you solve for this, you have as many systems of equations as there is variables to solve for, and then you can work this out. But we never really worked out all, like, you'll never get asked like a very complicated system of equations. At most, you'll have like two equations, and you have to like solve and isolate for variables. So that's what happened in the multi-dimensional case. Okay, and then we moved into the actually optimizing the machine learning problem we cared about, which was linear regression. And what did this look like, and how did we map it to an optimization problem? Where here it's like the supervised learning setting, everything's the same. You have features, but now the labels are these continuous things. Or not, well, they're continuous, but also they have some sense of order. So like, for instance, the price of houses. Then there's a function class, okay? And we're going to talk about how we define that in a second. You have your data set, and then you have this estimated loss. So we've seen all this. And your goal really is to find the function from your function class that's going to minimize the estimated loss. And then we said, how in the world are we going to search over functions? And the solution, as I had alluded to earlier, is going to be to define your function class in a very special way, such that every function in the function class can be described by some parameter. In this case, it's a linear function. So it's described by what is the slope plus the bias, right? This thing's a vector. Or I call it it's the weight vector. Okay. And the +1 is always for this bias term. So now, because of this, you have this wonderful thing that you can search over weight vectors. And if you do all that, you end up with a closed form solution for linear regression. So in linear regression, because of the way like things work out with this function class and the loss being the squared loss, you can actually like minimize over this estimated loss, set the derivative all the partial derivatives to 0, rearrange, and you get a solution. And that solution is this W hat vector. And this is the exact solution, the closed form solution. And it's like this linear algebra problem. You don't need to know like how to work this thing out. We didn't talk too much in detail, but you should understand that there is a closed form solution, and like the steps you get to that, you set all the partial derivatives to 0, and then if you solve that system of equations, it becomes this kind of thing. Okay, and then yeah, you can think of all these things as algorithms, as we had seen in assignments and so on. And the kind of cool thing with all the machine learning stuff is all the algorithms are really straightforward. There's really only two you've seen. It's like either there's a closed form solution, which is only the case for a lot of simple problems, or for most problems, you really need to use gradient descent, which is going to be the next thing I say. And in that case, you just like keep applying the same exact equation of updating the gradient, like updating the weights with the gradient. So the algorithms are all like very, very short. Yeah, and maybe one side note is like, what is where all the code comes from? You might ask, like, where's all the code coming from in these more complicated algorithms? It's like, how do you search over these different things called hyperparameters, like trying different step size and so on, and even just writing the code to define the function class. Like with the neural networks, there's all these layers and neurons and stuff, and that could take like 100 lines of just defining your neural network class or something. But then like the actual optimization is like a few lines. You just like do, yeah, the gradient descent stuff. Okay. So closed form solution, it's really the best fit to your data. It's like the best you can imagine. If you have a closed form solution and it doesn't cost too much computation to get, then you're fine. You're good to go. That's the kind of the dream. And okay, then we found that sometimes you're not so lucky and there is no closed form solution. That's like the main motivation for gradient descent. Then you do something called gradient descent, which is like an approximation to the closed form solution, or the true minimum. And the way you do this, the story was like, okay, we have a function, but like it doesn't have a closed form solution, but it's convex, right? Because we always assume things are convex. And like clearly it has a minimum. So how am I going to find this minimum? And the story was like, let's approximate it with some function that we know how to calculate the minimum. It actually has a closed form solution. And then use that kind of as the solution. That was the second order gradient descent story. It was like, let's approximate the original function with a second order function. Let's then find the minimum of this function. That was just take the derivative of this function and set it to 0, right? Derivative of that function, set it to 0. And if you do that, what you find is there is a solution. Unsurprisingly, you chose the function to have a solution. That solution is the following. And so this is the solution to find the minimum of that approximation to the true function. And then the idea was like, oh, this gives me a new like weight vector. Or in this case, it's 1D, a new weight. And what I can now do is use that as kind of my starting point to the approximation. So these approximations all have like a point at which you approximate at. And each time you get better points to approximate to your original function with. And so that's where the iteration comes from, the iterative procedure. And so you repeat this over and over again. This is each time, technically, I mean, not technically, it's exactly the solution to the minimizer of some second order polynomial, which is your approximation to the original function. And each time you're using better and better points to approximate from. Okay, so that was the story of gradient descent. Turns out the second order gradient descent is still kind of too expensive for people to compute, especially in multiple. Okay, let me get back to that point. Before saying that, I just want to note that, like, yeah, you keep doing this iteration over and over again, and as t approaches infinity, you're going to get to the actual solution, but for some finite amount of time, you can never really be certain that you have the true minimizer. Okay. So yeah, then turns out people think the second order stuff is too expensive, especially in multiple dimensions. And that's because this term here becomes this matrix, and it's very computationally expensive to compute. And so people do an even further approximation to things, which is instead of computing this 1 over the second derivative, and in general in multi-dimensions becomes like this inverse matrix called a Hessian. And if you, like, what you find is that you want to use this first order gradient descent, and that's just approximating this 1 over second derivative with a number. That's the step size. So that's the, yeah, you saw like a question like this on the midterm, which is like, are these equivalent if you set the step size to be 1 over the second derivative? And the answer is like, yes. That's the thing you're approximating. But usually you can't do that because you don't want to calculate the second derivative. But if you could, you would just get the thing back. Okay, so that's the thing you're doing with first order gradient descent. And yeah, the story is the same. There's this update rule. Now this thing replaces the 1 over second derivative. And yeah, you just iteratively compute this thing. It's important that you pick the step size correctly. If you don't pick it correctly, you can do this thing happens called diverging, where you take 2 big steps and you don't even make progress. So if you want your solution to get closer and closer to the true minimizer, you really need to pick a good step size, and you have to do a lot of iterations, a lot of epochs. Okay, that was the story. And for that reason, there's a lot of different ways to select step sizes. We saw actually some very simple ones in this course, and there are some rough ideas about why each one should work for the reasons it did. And I'm not going to ask like intuitions about why you picked which step size setting or like where these came from, but I could ask you to like at least compute what it would be at this epoch or like something like this, so you understand how they'd be used. And in practice, people really do end up using like they don't just, okay, sometimes people will use this constant step size, but there's some like slightly more complicated thing that people will use. And there's a lot of research to make like the equation as simple as possible, but still be as accurate as possible to this 1 over second derivative thing. Okay, and these are on the formula sheet, maybe. If they're not, then I would obviously tell you in the question. I don't remember. Okay, and then we moved on finally to how this applies to machine learning. In which case, okay, I should definitely get moving. Okay, so in which case the story was, what is the function we're minimizing? It's the estimated loss. So you do everything we saw in the optimization stuff, but now with this as your g function. Okay, and this was called batch gradient descent because this thing depended on all the data, the full batch of data. So the algorithm was literally like compute the gradient, take gradient steps. Visually, this is important. You've definitely seen this before. You should understand that the closed form solution is like the best fit. And with gradient descent, if you choose a good step size, what you will find is that as the iterations increase, so from like 0 to 5 to 10 epochs, you're getting a better and better fit to the closed form solution. Okay, then there was stuff about computation. I will almost, like if there's going to be at most one question about this, and it would be like pretty straightforward about just like comparing these things kind of like this. Like you're not going to need to know how much like computing matrix multiplications and outer products and stuff is, because we really didn't go over that. But if I told you like one thing, looks like this and one thing's like this, then like if D is less than this, you should be able to like take these steps to like work this out or something. Yeah, probably at most one question, if that. Okay. Mini batch gradient descent stuff, like we've seen a lot of this, I guess, on the midterm. It's like batch gradient descent, but now you have an estimate of the loss, but with smaller chunks of data. And the idea here is that now you can take more gradient steps, but each one of the gradients is like technically a worse estimate of the true losses gradient. That's the high level intuition. There's like notation and things like this, but yeah, we've seen this before. The real advantage is, yes, you can take m times t gradient steps as opposed to before in batch gradient descent where you just take t gradient steps. But the trade-off is that, once again, the estimates are worse. And so there's usually, like empirically, you just try a bunch of different values. For your batch size B, it gives you a different m value, the number of mini batches. And you just empirically evaluate and kind of pick the best one. That's what happens. And you have these two special cases. Batch size full thing, that's what we saw, batch gradient descent. And when batch size is 1, you get stochastic gradient descent. Okay. And then we moved on to the case where like we've only seen linear functions, but these might not be that good at modeling your data. So maybe we should consider more complicated functions. And kind of the simple ones to start with was polynomial functions. And they're polynomial, you apply a polynomial function to the features to get kind of like new features. And by new features, these would be like different multiples of the previous features to represent like squared relationships or cubic relationships, or when like scaling one actually then also affects another one simultaneously, and so on and so on. That was this phi feature map. And yeah, you should know like how to kind of like what it looks like for small values of p, and the fact that as you increase p, you get bigger and bigger function classes, this property. And bigger function classes means that optimizing over a big function class is always going to give you a smaller, or at least as small solution as before in terms of the estimated loss. So these are like two kind of important stories. Yeah. And so visually it looks like this. We got to this point of like increasing p, making p very, very large. You get a very, very complicated function that can fit your data very well. And so we thought that maybe we did something like we were kind of done at this point. You just make the function class really, really complicated. And the only thing you trade off is computation, because now you have this higher dimensional thing, and then you can fit the data really well. But we found that maybe that's not quite true. Okay. And before I get into that, I answer maybe one question here, which is, the question was something like, will some questions on this final depend on answers to previous questions? And the answer is probably yes, but like it won't be like a long dependence. So it might be like one question before, as you've seen before, which is like, with everything as defined before, like what's this? Yeah. Okay. Yeah, it won't be like 6 questions down the line. You know, you still needed the solution to the question before that. All right, so the story was that, yeah, like maybe fitting your data, the data set is not always going to give you the best possible solution. And we roughly saw that just by looking kind of at ERM, like imprecisely at the beginning, which is like, there's 2 things you need, right? Which is that, first of all, the function class is rich enough for you to actually have been able to make the true thing you want small, which is the expected loss. So making the function class bigger can actually make the true expected loss smaller, of course. And then the second thing is you want that the thing you actually minimize over, and then you output this f hat, this is the predictor output, and you're minimizing this L hat, that this value actually accurately represents the true expected loss value of that predictor. And so these were kind of the 2 things that we were battling with. And this kind of represented the approximation error, and this represented the estimation error. Okay. Lots of detail, or like things about why this makes sense and whatnot, but these are like the 2 kind of most important points that we got to, which is like thinking about where are the errors coming from in your objective, and then how can you change them, and then how can you like empirically look at it and decide what the right choice was. And yeah, there's these 3 errors you can break it up into, which is irreducible, approximation error, and estimation error. The irreducible error, usually you just say you can't like really change it, but if you really wanted to change it, what you would do is you would go and gather new data, and the data should be in the way that the features themselves are new and more informative. So like the classic example is if you have like just the number of rooms of a house, you would want to go gather more information like the number of people that live in the house, where it's located, and so on. And that will allow you to actually improve this irreducible error, which is just like in the inherent noise in the data, because you don't have enough information about the house to make the correct prediction. Okay, but those that we barely talk about in machine learning, and we really care about changing these two. And the story was that estimation error, you can always, like, increasing data will always be a good idea. So like you can always increase n if you can, and that will cause for estimation error to go down. And then there's a battle in terms of the function class of like estimation and approximation error, which is in general picking a more complicated function class is going to cause estimation error to increase. There's much more functions to pick between, and this causes like this f hat, kind of the model or the predictor that ends up being chosen, to be like very dependent on the data, to overfit the data very strongly, and this is far from the best possible fit to new data. That's kind of the story. And the approximation error is very obvious why it would go down if you decrease the function class size or increase the function class size. Just by the definition that f star will become a better and better minimizer of something if f gets larger. That's all I want to say there. We've talked about this a lot. There is this plot. I don't think I have time to go over all the details, but we've gone over all these details and we've seen it on the midterms. So yeah, you should understand like all these different kind of parts and stuff. Okay. The main point was that like, maybe I say one thing about this plot. The thing you care about at the end of the day is this expectation over the expected loss of your predictor, and the predictor can change with data. So if you could have this curve, what you would do is you would pick the polynomial degree p. So here we're plotting the polynomial degree. This is like the complexity of the function class. So if you had this curve, you would pick the complexity of the function class, the polynomial degree p, that minimizes the thing you really care about. This is the thing you care about. Okay. That's the thing on the left-hand side, is why I'm saying you care about. This is the thing on the left-hand side. And these are all other like things that can kind of give you information about that. So what you do is you don't have this thing, but you can get an estimate of it with new data. And that new data, it's like new data in the sense that you haven't used it for training your model, is called a test set. And so yeah, you like separate your data into this thing called training, which you use for your learner, and then a separate thing called testing data, which is going to be used to estimate this true objective we actually care to make small. And so yeah, so usually the only thing you really need to plot is this, which is the estimated loss using the test data of the actual predictor you output. You plot this thing. This is just an estimate of the true thing you want, which is that expectation over all data sets. But you get that estimate, and then you plot this thing, and then you pick the predictor that minimizes it. And this curve should roughly resemble this one. While the one that's, if you plot the estimated loss based on training data, what you always find is that it's always decreasing, because you're just fitting the data better and better because you're picking more and more complicated functions. Okay, so point is, this is not representative of how well it's really doing on new data. And the reasons why is, once again, these different errors are coming up, and one is starting to dominate like another one, and so on. Okay, so you should understand all these different things, like what changes them, if you could see these plots, like what happens, and so on. And then there's another way to talk about like where is error coming from in the predictor you output, and that is this bias and variance stuff. And with this bias and variance stuff, it turns out to be like the same story as expectation and approximation error in the case that you have no regularization. Okay, so we haven't covered regularization up to here yet. And so in this case, yeah, they're the same and everything is fine, and the story, like everything is the same story. But then when you add regularization, the story kind of changes. And bias and variance is an important thing to talk about then. That's like when bias and variance kind of is very useful. And in a lot of real machine learning stuff, people actually do use regularization. It's like a smoother way to change the complexity of the predictor that your learner is going to output. And so that's like kind of the benefit of it over this polynomial degree. Maybe that's all I say. And then you have similar curves where now we talk about different, like we talk about the bias and variance. But you can plot similar things, and then you would pick this polynomial degree, and you have this test set and train set. Okay, that's all I want to say about that. And I want to mention there's like, I did post this video on YouTube, kind of, there's a section added to the course notes called section 7.6. It goes over these different things in a one-page thing. It has this table. I guess this is really helpful for what you should know about like the different cases on the midterm and understand these different cases. And I talk about it in the video and so on. So you can ask questions about that after. Okay. Now let's get into more stuff. Okay, I think we'll actually be okay with time now. So maximum likelihood estimation and maximum a posteriori. What was like the story here? And the story here was that you could try predict there's not only maybe one way to produce a predictor. Like so far we've seen this ERM learner algorithm to produce models or to output models. And now it's based on estimating the expected loss. But another idea is to just look at what we want F base. Like that's the best we could ever imagine to do. So let's just look at what is the equation of F base and try to approximate some terms in the equation to get F base. And so this is the points at which if we worked out the details of this, when you expand this out, you would have like an integral and a sum or a double integral. And this is where the integral stuff actually comes in handy and stuff. But if you word loss, which we don't do in this class, and maybe to be added in future courses, I don't know. Feedback again, if you guys really wanted to see this, maybe this should be added, but there are some details. You work that out, you get an equation like this, and the important thing to note is that there is this conditional PDF, because we're in the regression setting, so this is really a PDF, right? Y is continuous. Okay, so then that gives you this motivation of like, let's estimate this guy, plug it into here and evaluate the integral, and then use that as our estimate of F base. Yeah, that should make some sense. But another way this can be intuitively introduced without this like formal justification to it is people will say like, if I want to estimate y given x, which is kind of like what my function is going to do, right? My model is like taking in x and I want to predict y's. What I can do is just learn the distribution of y given x, which is what this PDF gives you, right? It gives you the distribution of y given x. And then like maybe one thing that would make some sense is to just output the expected value, right? Like at every value of x, there's this plot. Where is the plot? Yeah. At every value of x, there's like some distribution. This is the thing you learn. And so you're like, oh, I know that there's like all sorts of different values it could take, but maybe the one that's the best output for my predictor or my model is just the one that's like the most likely, or sorry, that happens the most on average, kind of. So that's the expected value. So that's what you choose to do, really. That's what happens here. You take the expected value of the distribution of y given x. But there's some like formal reasoning why this is a good idea, which is this. And the story with this maximum likelihood stuff was just some way to estimate these PDFs or PMFs. And there you have like same setup as a supervised learning. You have this like data set, they're all IID. And the way you do it is you're trying to find this parameter WMLE, the maximum likelihood parameter, that maximizes this likelihood function, which you can think of as like how likely it is to see the data given this parameter. And this parameter will change this corresponding conditional PDF. Okay, so and you can, once again, you can always think of PDFs as representing a distribution. So like for different distributions, the data is more likely, and under other ones, it's less likely. So you want to pick the distribution for which that data would have been the most likely. Okay, so that's what you do, and then there's like some steps to work it out, and turns out taking logarithms is very helpful because when you expand this thing out, it turns out to be the product of a bunch of data points, and then you can use the property of logarithms, which we've seen very many times, that the log of the products is the sum of the logarithms. Just like mathematical convenience, once again, this log. Okay. And that was the story. And then we applied this to the actual machine learning case where we had this like conditional stuff. We assumed that y given x has some conditional distribution. This was just an assumption. For some reason, we chose it was normally distributed. Like we didn't talk about y, but if we did this, and then we assumed the mean was this linear function. Okay, there's a function of x, which makes some sense. For different x's, you have a different distribution. And for some reason, the variance is just fixed as 1. If you work all that out, this MLE stuff, you end up finding that this is the thing you're trying to minimize in MLE. After you like plug it in to this likelihood function and simplify, you get this. And then you notice, oh, this thing is almost like the estimated loss we've seen before. If I just multiply it by 1 over n, it turns out that's totally fine when I'm minimizing something because the 1 over n really doesn't change anything for a minimization problem. So if I just add that, then I get this like the thing we've always been doing with ERM. And so you get this like equivalence thing, which is that the maximum likelihood weight is the same as the one you used for ERM. So there was this nice equivalence. Then there was this map stuff, which was another way of thinking about how to learn the parameter describing some PDF or PMF, which then describes the distribution, of course. And there you think of it in this way, which is like, maybe you have some like prior knowledge on your parameter. Okay, so you know that like, oh, it's probably not going to be like really, really large numbers. Maybe it's like small. This is where the intuition of like, if the parameter then describes like this like linear function, and you think the linear function should, or sorry, it's like describes the weights multiplying maybe a polynomial function, and you think that that polynomial shouldn't be too complicated, then these weights might be really close to 0 or something. That was like the intuition we had of why we would put a prior on something. Okay. For the exam, what do you need to know? What you need to know is that for the map stuff, you start with this. This is given in your formula sheet. And I guess these steps are also given, which is that if you can then expand this using Bayes' rule. I think it's these two steps, actually. This is Bayes' rule, actually just jumps to this. And then you realize that this thing, we're trying to find the weight vector, or the parameter W, that makes this the largest. The denominator doesn't matter, and so you get to here. So I guess this is the final thing you see on your formula sheet. I guess you should know these steps. You could be asked, like, how did you get there or something? And then when you apply the log, this thing splits up into the sum. So this is like the kind of your starting point with map, where you have what ends up being your likelihood function, the thing you've seen from before. So you can imagine in a question, if you've worked out the likelihood and then you get asked about map stuff, you can save a lot of time, and it's probably going to be like implicit that you should know this in the questions, that like you reuse what you calculated in the previous question, because it's going to come up right here. And then all you have to do is calculate this term or something like that. Okay, so that's the like, all there is this extra prior, this prior that then multiplies the likelihood, kind of weighting it by your prior knowledge about what the parameter should be. That's the interpretation. Okay, there's these cases. I maybe skip them. Yeah, and then once again, this applies to the machine learning case, where now the thing you're assuming has this normal distribution is the conditional of the labels given the features. Okay, yeah, then you work out all these things. Okay, well, okay, what's the actual assumption we make on the prior in this case of supervised learning? Well, the assumption is that each one of these weights in the weight, so the weight vector has a bunch of weights, d plus 1 weights. You're going to make an assumption about what is the distribution of each weight. And the assumption that we're going to make for, I don't know, for whatever reason, is that it's normally distributed with 0 mean and some variance. And it's going to be, you can change the lambda to change the variance that you assume in your prior. And this maybe somehow relates that you think your weights should be close to 0, that they shouldn't be too large for some reason. Okay, so if you make that assumption, then if you work out this map stuff, you get to an equation that looks like this. And then the nice part of this is that it looks just like the regularized estimated loss, except it's not, once again, it doesn't have this like 1 over n factor in front. So another way to think about it is, if you take this regularized thing, then it's equal to this term up here, but if you multiply this by n, because this guy had a 1 over n term. Okay, but at the end, that doesn't change the minimization problem, so we say these two are equal, even without these factors. Okay, so there's this relationship of the two. That like, that turns out that this thing I told you, which was kind of a leap of faith with the regularization, you're adding this like penalty business, can be thought of as having prior knowledge that the weight should be close to 0. And if you have that, this problem would actually kind of like force you to have the weights close to 0 in this exact same penalty. And then you can change your prior to like the Laplace prior, and that will change your regularization. And people do this in different cases and has different effects. And we didn't talk about it in this class, but yeah, you could play around with all sorts of different priors for various reasons, and then see what the penalty is, and then see where it works, and so on and so on. And lots of research goes into these kind of things. Okay, we have 20 minutes to now talk about what we learned in the second half after the midterm. Well, I don't know if it's the second half, but the stuff after the midterm, which was 4 lectures. Okay, someone's still talking about what happens if you get one question wrong. Will it affect the others? If you like, and the answer is like, so I don't really, like, I can't, like, I can assure you that there's probably going to be at least one question that depends on others. And if you do the calculation wrong on the other one, then there might be a chance that that's going to depend on the next question. I will try kind of my best to make it so that like, if you didn't, like, it maybe doesn't depend that much, but yeah, that's kind of part of the challenge. Like that, I think that's okay. Like, I don't know, like 1-2 questions you can expect to have this kind of dependence. But I haven't written the final exam, so I don't know. I unfortunately can't tell you the exact how many questions will have this. But it'll be like probably similar to the number the midterm had. Okay. And this would be kind of like, I don't know, other exams that have these like part A, part B, part C, you know, and then like they will have some sort of dependence on each other. Okay. So after the midterm, we finally started talking about something other than regression, linear polynomial regression, and that was classification. And the story was, let's just start doing what we were always doing and do ERM. And we tried that with the 0-1 loss. And like very quickly, what I told you is that you have some problems because now the function you're going to try to minimize, that's what you're doing in ERM here. Oh, okay. I didn't write it out, but in ERM, you're trying to minimize this estimated loss. If you try to do that, you're going to have some problems because it's not continuous. First, because the loss isn't continuous. But even if you then chose a good loss, if you had a predictor that predicts either 0 or exactly 1, you would also still have problems because if you take that derivative, it's still not continuous. So there's kind of two things what we're going to need to do is change the predictor to predict somehow continuous values, to not make these sudden jumps between predicting 0 and then immediately 1, and change the loss. And that, like, we worked through a bunch of things, but what the story was is the way we achieved this is to make the loss these like cross entropy losses, which are continuous with respect to their variables, and to pick predictors that are not predicting 0 or 1, but instead predicting probabilities of that class or of the classes. And that has like a nice continuous, that's a continuous function, and there that allows you to take derivatives and so on. And all that being said is we got back to regression after all. Okay. So we struggled with this, and then we wanted to like somehow have a more, let's say, principled way of finding out what is our loss function and what should f be predicting and so on and so on. So then we tried instead of just like making a guess, like we could have just at this point said, okay, let's choose something that's not 0-1 loss, that is like kind of continuous. And then let's pick a function that doesn't predict 0 and 1 exactly, but like has some continuous interpretation. And you would be like, okay, I guess, and see what happens. But we took another approach, which is like you start with this f-Bayes expression, which is f-Bayes is the best possible predictor that minimizes the expected loss. And then then you can work out what this is. And here I didn't write, which is like you assume 0-1 loss, because that's really what you're trying to minimize. And you plug that into here. And once again, that would be like, here you would have like an integral and a sum if you expand this definition, because it's an expected value over two variables, like the features and the labels, kind of summed up. You have this integral and the sum and whatever. And if you simplify, you get this. This is the important part. And this is on your formula sheet that if you assume the 0-1 loss, f-Bayes becomes not the expected value of y given x, but the y, the label, that has the largest probability of kind of occurring. Like the largest, yeah. And that's, once again, similar to this linear regression setting. There's another interpretation without doing this like principled approach of what happened here, which is like, if you want to predict the class, one way you might think of doing this is like, let's learn the distribution of every single class given a feature. So like, I have a feature, I want to know what is the true probability that I get class 8, class 1, class 2, class 3, up to whatever. And now if I have all these probabilities, why don't I just pick the one that is the largest? So that's sometimes how people will also introduce this kind of thing. They'll just say like, if I want to predict a class, why don't I just learn the distribution of every single class, which is like this probability here, and then just output the one that has the highest probability. But f-Bayes tells you that's actually the best thing to do. So all that's left is to learn this distribution. And so, yeah, we do this with MLE. That was the story. And we did it with two separate, since it kind of gets, like, as you saw, it gets kind of complicated with multiple classes. We started with the simpler case of 2 classes. We worked out this MLE thing. And the big difference from before is that we assume that the distribution of y given x is not normally distributed. That would be really weird because the normal distribution is a distribution over like all real numbers. But here, y can only take 2 numbers. So you should probably choose something different. So you choose the Bernoulli. And the Bernoulli has a parameter that you need to estimate. And so since that parameter is between 0 and 1, you choose a function appropriate to that, which is like this sigmoid function or this logistic function that actually squishes down your linear function to 0 and 1. That was the rough story. This was like the big difference of this and the linear regression stuff with MLE. Okay, after that, everything, like the story of solving MLE was all the same, really. The only thing that changed was that the conditional PMF now is the following, while before we had a conditional PDF for the normal distribution. The only thing that changed when you work things out is literally just plugging in that equation, which gets plugged. Okay, this has a lot of steps in it, but when you plugged it in, that's the only thing that changed. And so since they're different functions, when you simplify things, you also get a different thing you're minimizing. So you get to this point, which is WMLE, you work through all these steps, you get to this, and you find that you're trying to like minimize this. So we minimized it using gradient descent because I told you it doesn't have a closed form solution. So you should like understand how to work out some gradients and stuff like this. So this kind of a function. And we did that in class, and we found that okay, there is some gradient. Okay, fine. You use that gradient, and then you take gradient steps with respect to it, just like you did for the case of the linear regression stuff. Okay, so that was the story there. So here, like slightly more formally, what I said before of like, what are you doing with this F-Bayes approximation? And like, you learn these probabilities, you pick the largest one. Like what, at the end of the day, we wanted something that actually predicts what the class is, right? So like more formally, this is written as you have some function that's going to take in data and actually outputs a function, a predictor or a model that takes in as input features and actually outputs 0, 1. So how is that function going to do that? That's the thing you actually did need at the end. The way it's going to do that is it's going to make use of the thing we just learned, which is those probabilities. And the story was, yeah, you had F-Bayes, this we had from above. We approximated this just now, this conditional PMF. Plug that in, that's our approximation here. And then we're going to take this argmax. There's only 2 classes. And that gives you F binary. Okay, that's so this thing is actually a thing that predicts 0 and 1s and stuff. But notice how we didn't like explicitly optimize over it using derivatives or anything like that. Since we have very little classes, and this is often the assumption for this kind of thing, is that this argmax is really easy to compute because you just like calculate this for 2 numbers, and then you can calculate this. And the hard thing to do is calculate the probabilities of each one of these y's. And that would be what FMLE does. FMLE actually finds this probability of each of these y's. It actually gives you the distribution of each of the y's, the conditional distribution. Okay. That's all that was. And then there was like some ways to think about what is happening with these decision boundaries and stuff. And you saw that in the assignment 7. And I guess I will talk about it a little bit in the tutorial today. Similar with like working out this and the comparison to logistics. So today's tutorial, I'll be talking mainly about how to think of this, or I guess it's the next slide, how to think of that MLE thing as just a regression problem, this logistic regression one. Okay, so these will be important things to understand for sure. And I will go over it in the tutorial in much more detail because that's all it's focused on. So yeah, as you saw above, you can think of it turns out you can think of what we were doing in MLE as just a regression problem where the loss function is this cross entropy loss, and there's like where it came from is just looking at what this thing was. Like, well, you look at this whole term and you're like, oh, this looks awfully close to an estimated loss. I have a sum over n here. I could just put in 1 over n. That's not going to change the minimization. So all that's left for me to think about this as a regression problem is to just map this to a loss function. I somehow need to map this thing to a loss function. The loss function is a function of a prediction and the true label. What is the prediction in this function and what is the true label? That's not too hard to map to something. You look, this is like the true label, these y's. And then what is your prediction? Your prediction will be called this thing. And then what's left is just give it an interpretation of what these objects are. And you call this like it's not even an interpretation. It's like this thing is exactly the thing representing the parameter, which is equal to the probability of y equals 1. And then this thing would be like the true probability. And so yeah, so that's the mapping to the logistic regression. After you have that loss function in the function class, I mean, it's the same story as you've always seen with ERM. And this is just showing the equivalence that we've seen of MLE and ERM. Okay. Then with multi-class classification, things got a little bit more complicated because we have k-1 classes. And then we tried to work out MLE again, right? But the thing that changed was now you don't use a Bernoulli distribution for this because you don't only have 2 classes. You now have k-1 classes. So you use like what is called a generalization really of a Bernoulli, where now you have a parameter for the probability of each one of the labels. For Bernoulli, you only had a parameter for the label of 1, and you could immediately imply the probability of 0. Technically here, you don't actually need this parameter. So sometimes people won't even include, and they'll say, oh, you actually only need k minus 1 parameters, because you could always infer the last one. But we do the like more, this is probably more commonly done, where you just estimate all of them. But once again, there's a little bit of a discussion in the notes, and maybe you could be asked like one question about like how this parameter is really redundant, how you can deduce it from all the others. And that's just because of the fact that like all these parameters have to sum to 1. I guess I don't have it on this picture, but like in a categorical distribution, all of these have to sum to 1. Which makes sense. Like those are the probabilities of every class. You better hope they sum to 1. And we need to estimate all of these guys. You have k minus 1 things to estimate. They have to sum to 1, and they have to be between 0 and 1. So you use some function that has these kind of properties, and that's where the softmax comes from. It takes in some numbers. Not actually these. Okay, it takes in some numbers, which are these things, k minus 1 numbers, and it makes them into a probability distribution, which we saw like maybe some more intuition about this at the start of last class. I talked about how you can think of the softmax as just taking in k minus 1 numbers, making those numbers positive, and then making them sum to 1 by what is called normalizing by the sum of all of them. And that's all that really happens. It's just trying to ensure this property. And then once we have that, we solve the MLE problem, which is you start with the negative log likelihood, you plug in this expression for your thing, for the probabilities you're estimating, and then you work out, and there's lots of math. And this was probably the most complicated set of math we did in this course, I guess for sure. And then it had some partial derivatives, and you get to the gradient as before. Because once again, this thing did not have a closed form solution. That was the rough story. And as I guess you've noticed, working out these partial derivatives and stuff can get very complicated. I will go over this again in the tutorial today about like slowly, I guess, talking about how to interpret this and why in the softmax thing you might want to use one hot vector here and things like this. Okay, and then all that gave you what is the actual learner we want, which is this thing that's going to actually output numbers like 0, 1, 2, what is your class? And that is just very straightforward, which is if you started with this F base thing, which is the following, you then plug in your approximation of the PMF. That's this thing based on all of these parameters you learned from MLE. And then, okay, I just plugged in what the definition of this is, which is the softmax. And that gives you the actual multi-class predictor. So the multi-class predictor is saying, let's get an estimate of the conditional, and here the PMF is actually exactly equal to the distribution. Like PMFs are always equal to distributions, actually, which is what is, like, you get the conditional probability distribution of y given some x's. So you now know the probability of every label, y, or an estimate of what that probability should be. And if you have that and you believe that estimate is good, well, it tells you that what you should do is pick the label or the class that has the highest probability. So that is where your multi-class predictor is. And all the challenge and difficulty is in learning this guy, which is really learning these parameters for it. Once you have that, then you just have this simple thing of just take the argmax of like some small number of objects. I guess in language modeling, maybe this is not so, that this like argmax is not so small. Maybe there's like 50,000 words, but still it's just like one loop to find it. Okay. Yeah, and then there's this relationship to softmax regression where you once again look up here. You notice that this thing can be represented as an estimated loss, where this thing is a loss function, and it's a bit more complicated to do the mapping between what is the labels and what is the thing, the predictor here. But after you do that, you get, you have a loss function, you have a function class, and then you just can do ERM and they're equivalent. Okay, and then there was like a brief discussion in the notes. I would recommend maybe reading over some of this. Maybe there'll be like one question about relating categorical to Bernoulli distributions and how those things are equal. Okay. Last two parts, neural networks and language models. And so neural networks, I can assure you there'll be some questions about this. And it's largely about just like understanding what the networks, like how many ways does a network have, like how many like neurons maybe does this thing have, like some simple networks. If I give you some weights and stuff, like how does the output, like what is, do you understand the computation through it? Or what you'll see in the exercises, I guess also in the tutorial, and I posted them, is like, you might be asked like, I have a function, can you give me a neural network? that is equal to that function, like maybe adding numbers or subtracting numbers or something like this. And these are all will be very easy. It's just like that you understand how to like set the weights or something like this. And you notice that like, oh, when I set the weights, these things get added, and then I can maybe like exponent, whatever, to apply some function and then add them together again and so on. Like you wouldn't need more than like 2-3 layers but yeah, these are all very useful to get the intuition for neural networks. So all I really have to say on this about neural networks here is that, yeah, the neural networks look like this. They have these layers, they have these neurons, and then they have activation functions, and then they have weights. And when you tell me all those 4 things, I have a neural network. I know exactly what it looks like, and I know exactly, if you give me some input, I can tell you exactly what the output is going to be. And then there's equations that describe it, which I'm not going to go over, but the short story was like these things get multiplied by weights, which then get applied through activation functions, which then themselves get multiplied by weights, which get applied to activation functions, and so on until the output. Okay. And then, yeah, the way you optimize these things, like we didn't go through calculating the derivatives, but the story was the same as what we've always seen, which is it's really quite lovely. You just like define your loss function. You then choose the function class to now be neural networks. And then you just run ERM, and then you just need to calculate these gradients. There's a lot of weight vectors now, but you just need to calculate all those gradients. And if you could do that, you should understand that you would be like improving the network's weights over and over, and then finally output a better network at the end. And once again, we did not calculate this gradient in class. You probably could, if we spend one whole class, you could work it out, and in future courses you see this, but it's just some chain rules, really. There's like nothing that you can't work out with the tools you've learned. Okay, 2 notes. Usually you don't end up with closed form solutions with these neural networks, and that the estimated loss is usually not convex. And then that's kind of where the edge of where we stopped with the optimization stuff. And further classes usually talk about how to optimize non-convex things and why it would make sense in places and so on. Final thing is these language models. Oh, maybe one last thing you should know about neural networks is that like the features, as you pass through the features, they get better and better kind of, or pass through the activations, you could think of them as better and better features, which we saw with like understanding better and better, like more complex parts of like a picture of a cat or something. That's an important thing to understand. Okay, finally, language models. What would you need to know about these language models? Well, like probably not that many complicated things because we didn't really do much technical things about language models, but you should know the general idea of like that. Okay, we only talked about this case of generating text, so that would mean like you had your goal is like you had some input text and you want to output some sequence of text. And then we talked about the specific ways of achieving this is these autoregressive models that do this one word at a time. And these words, I should really be saying, are tokens. Okay, so they generate one token at a time, and then eventually you get to the end and it tells you this is the end. I think it's the end of my generation. And so you could just have a model that outputs every one of these tokens, but that once again is this uncontinuous, like you have this non-continuous model or output. And so optimizing over that becomes challenging. And so what we do is what we saw in the multi-class classification case, where we're not going to choose our predictor or our function class to be like outputting the actual class, but instead we're going to output a vector of probabilities where each index represents the probability of every token. And that becomes much easier to optimize, is basically the story. So yeah, that's the thing we actually find, this F prob. So we're trying to find the best weights that describe, or okay, the best, we're going to see what the weights are in a second, but the best kind of function, the best F probability function for doing this. And the way this will look like is that this F prob, so that's this blue box, this guy here, takes in as input X, as you should expect the feature, and now it needs to output a probability vector that has K probabilities. These are all the probabilities for each one of the tokens, one by one. This would be like the probability of the first token, second, and up to the K. And the way you do this is you just have some function that first outputs K numbers from negative to positive infinity, which will often be a neural network. And we saw like the neural networks can really represent everything, every function we saw before in some way. And then you pass it through the softmax to make it a probability. So all that's left is to just find the weights that describe this. There's no other parameters here. Like this is all determined, like there's no weights or anything here. So this is if I find the weights that describe this neural network, I have found this function. And if I find good weights, which our learner will hopefully output for us, then I will have a good function for predicting probabilities, a good model. Yeah, so that was the main thing. And then maybe one last note about these language models is that, like, that's the whole story. All you need to understand now is, like, how are you going to represent text as a vector in RD+1? And you do this through this embedding function. So you should understand that the embedding function takes in tokens. This is E, the embedding function takes in tokens and produces vectors. And then we had this interpretation of what these vectors mean. And then how do you use this embedding function? Well, you have a sequence of tokens. So you pass every token through the embedding function. Then you concatenate all of those embeddings. And now you have a vector of dimension D, where D is number of tokens times the dimension of every embedding. Okay. So that's the story of that there's like an example of how you break up your data set. That should be, you should like be comfortable with that. And then, yeah, similar to the neural network stuff, the way you optimize these models is just, as we saw, is just a neural network with the softmax applied. So now your function class is these functions that produce vectors of probability. And all you need to do is optimize over this neural network of some fixed architecture. And this neural network is defined by some set of weight matrices. So all that's left to do is do ERM by doing gradient descent over these weight matrices. So once again, we always resort to searching over functions as searching over weight vectors that describe the functions. And that is all. So that's what I guess you should expect. And maybe I'll answer one or two more questions, which is like, yeah, I guess I don't think I can answer any of these right now, but if you ask on Piazza, I will hopefully answer them. Okay, I end the recording here. So thank you, everyone.